and again, welcome to Foundations of Algorithms for the last session of week 1. As you'll remember, at the end of the last lecture, we were talking a bit about how to get started in C. But unlike in other programming languages that you might have seen before, we were fussing a lot over the types of data that we were actually feeding into our program, whether it was a plain number or whether it was a number with a decimal point. And as we'll soon discover, in C, we're actually going to be required to always specify what kind of information we're giving the computer to deal with. Now, why would we have to do this? Why does the computer need to distinguish between different types of information? Why can't the computer just understand automatically if it's a number, or if it's a letter, or if it's a number with a decimal point? Why might we have an assistant? Now, where's my beautiful assistant, Tracy? You want to take some feedback from the crowd? Why does our computer need to be told about what type of data we're feeding into it? And it was, don't tell me, that was Jack. Yes.
Because different data types require different amounts of memory to store how much, like an integer has, there's other information, but like decimals, there's more information there, so it just like requires an amount of space for those two objects.
So you're very much on the right track here. Remember, at the end of last lecture, we were talking about abstraction. That if I look for files and folders inside the computer, they're not actually there. What actually is there is a whole lot of tiny, tiny magnetized regions. And if we want our computer to deal intelligently with that, we're going to have to tell it how many of those magnetized regions represent each given piece of information. And different types of information might require different amounts of those little magnetized regions. But you might ask, why do we do this in the first place? Why not just let every piece of information use the amount of space that it needs? Well, we'll get to that soon. And it turns out the answer is really interesting, not just from a computer science perspective, but again, what it's going to tell us about the way that algorithms work and some deeper facts about the very nature of computation, the nature of physics, and the nature of the universe. So in C, we're going to have all of our different operators, and these are essentially just the same kinds of operations you're used to in mathematics, plus or minus a few extra. Now C has a lot of these built in, and so we're only going to worry about a subset, at least at this moment in the class. So the normal mathematical operators, plus, minus, multiply, divided by, and then we also have this modulo operator, which we'll talk about soon. And then we will also talk about these comparison operators that work on pairs of values. So which one of these values is bigger than the other? Are these two things equal? Are these two not equal? Now, because many of you already have some programming experience before, I'm not going to go exhaustively through each of these operators. We'll see them as we use them in your tutorials and in this lecture. But if you have any questions, of course, feel free to ask on Ed, ask our teaching fellows, or come up to me after class and ask. One of the types that we're going to be learning about today, one of the most fundamental ones, is the letter. Now, in computer science speak, instead of calling them letters, we call them characters. Why? Well, because some of the letters that we're going to use aren't really letters at all. They're going to be symbols. So, for example, shout out one kind of character that's not a letter for me. Just shout it out. Exclamation point. At. Hashtag. What about something that you use in your text messages?
Emojis.
Emojis. So emojis are another really nice example of a character that's not a letter. Now, unfortunately, if we want to represent emojis, we're going to have to use a fairly big space to store all them, because there are lots and lots and lots of emojis. So for now, we're going to restrict ourselves to a much smaller set that just contains the letters, lowercase, uppercase, basic punctuation, spaces, tabs, question marks, semicolons, etc., etc. And we're going to call these ASCII characters. Now, ASCII is short for the American Standard Code for Information Interchange. Now, what does it mean by code here? Well, a code is a way of communicating to the computer what combination of ones and zeros, or what combination of magnetized regions and non-magnetized regions correspond to what letters. Now, again, if I open up my computer and dig in and you've entered the letter A into the computer's memory, nowhere in there is the letter A. Again, we've just got these magnetized regions. So we have to decide what combinations of regions is going to represent the letter A. So we're going to shorten our character type to just char and see if we want to use it. And so yesterday we saw int for integers, whole numbers. we saw double for numbers with decimal points, and now we're introducing char to store our letters and our basic punctuation types. This is what the basic table looks like. You don't have to memorize this. Of course, it would be kind of fun if you came to class having learned it all, and I could quiz you on it sometime. Not for assessment, just for fun. But you'll see that all the way over there at 65, we have our capital A, and then at 97, we have our lowercase a. So now I have a question for you. What would happen if I were to do 53 minus 3? And not Jack. It was James. Yeah, so 53 minus 3 is actually 2 in this system. How does that work? Why? That seems kind of counterintuitive. Isn't 53 a number and... Yeah?
Well, the computer doesn't know the difference between the numbers.
Okay, bring the microphone down. And your name again was Blake?
Yes. The computer doesn't know the difference between the number and the character. It's all stored as bits or bytes. So 53 is 5 and the number 53.
So in this case, we have this interesting thing going on, this kind of mapping between letters as symbols, as like pictures. So you can imagine the letter A is just a picture that has like a little triangle and then a dash in between. Just like the number 5 you can represent as a picture. But aside from being a picture, we can also store a number inside the computer that tells the computer, print out the picture that looks like the number 5. So in this case, we're using the char type to map certain numbers, certain bits and arrangements in the computer's memory, which we can talk about as their numerical representation. We can represent those as the pictures that they map to. So in this case, the number 53 maps to a picture that looks like the digit 5. Now you can imagine if you were representing numbers in a script that writes numbers in a different way. These are Arabic numerals, but there are other ways of writing numbers. You could have 53 still map into the number 5, but the picture for it would look different. And so what char is doing is it's allowing us to represent pictures in these two different ways, and these pictures are going to represent letters, because those are the types of pictures that humans interact with probably the most out of any other. So easy, we're good, but how about some maths? Now let's talk back about the number types that we were talking about yesterday, and this is where things are going to get a little mind-boggling. So all of you have probably used one of these before, I hope so at least. This is a clock. Yes, okay, so good, I still haven't lost the audience yet. This is a clock, but the clock can't count very high. I'm a little frustrated with my clock. It only goes up to 12. And unfortunately, this is also representative of how our computer is going to work. Now, I promise you this computer here can count a little higher than 12, but it still has a limit. And so what I'm essentially going to ask for a bit of today's lecture is, how high can my computer count? Does anyone have an idea of how high my computer can count? It's this M1 MacBook over here. 2 million? Any other guesses? 2 to the 64. Any other guesses? How high can my computer count up to?
1.
1? Okay, who said that one? Up the back there. That was a fun guess. That's fine, Trace. So let's go a little bit more into our exploration and see how high our computers can really count. So one answer that I heard was 2 to the 64, something that has to do with the number of bits that our computer naturally represents. And when I say naturally represents, if you can imagine a circuit, and you can imagine a circuit with a certain number of wires, and each wire is used for a different bit, a different 1 or a 0, a different charged or non-charged region inside the computer, and our computer is naturally going to have circuits built on a certain number of sets of wires at once. So in older computers, from, let's say, if you picked up a computer from the 1990s or the early 2000s, most of the operations would rely on 32 wires at once. Now, of course, if you actually look in there, the alignment is a little more complicated than just 32 wires going in at one position, but that's generally how you can think of it. And what this means is any mathematical operation you do that relies on only 32 ones and zeros is going to be really fast. And anything that relies on more than 32 or fewer than 32 wires, well, you're going to have to come up with a way to match those operations that you're doing fast with the 32 into some representation that takes, say, 55. If you want to represent a number that would take more than 32 y's. Now, I think, Blake, you said it before. Was it, or you were saying it's 2 to the 64? Where does the 2 come from? What are you talking about there?
Because there's 2 states, 1 and 0, and with 64 of those, you have 2 to the 64 different sets.
So let's slow that down a little. Let's say I have 1 wire. How many numbers can I represent?
2.
I can represent 2 numbers. What are the numbers?
On and off, 1 and 0.
0 and 1. Okay, now I'll give you another wire.
Represent 4.
Okay, so walk me through that. How many states can I represent with the first wire?
2.
Yeah, and how many can I represent with the other 2?
4.
Well, just with the second wire?
1.
Another 2.
Another 2.
So I have on and off on this switch and on and off on that switch. And now if you're imagining, I'm flipping switches, I can have this one on, that one on, this one on, that one off, that one off, that one on, that one off, that one off. So it builds up multiplicatively. So for every wire you add, you multiply the number of numbers that you can make by 2. So 1 wire, we have 2 possible numbers. 2 wires, we have 4 numbers. 3 wires, we have 8 wires. And if I have 32 wires, then I can get
2 to the 30.
2 to the 32, which is about, it's about 4 billion, yeah. When I say how high can my computer count, one answer would be, well, it depends on how it's set up with these wires. So one answer could be, it can count up to 2 to the 32 in this case, or 2 to the 32 minus 1, because we have to save one of those numbers for, who said that over there?
0.
0. Finn says 0. So we have to save our very first number for 0, otherwise we'll only have the numbers up to 1, and then all the way to 2 to the 32. So we actually have 2 to the 32 minus 1 is the largest number that we can count in this system. Or if you're on a modern computer, which now uses 64 wires, then it would be 2 to the 64 minus 1. Yeah. So that's how high we can count, in one sense of the word. But you know, that seems a little small. Again, Zane is back in the room today, and he's a physicist, so he wants to talk about really big things. Astronomical numbers, numbers bigger than 2 to the 64. And so that gives us a bit of a problem. What are we going to do if we've only got 2 to the 32 wires? Well, let's think about our representation here. So one way of doing this would just be to count upwards. So we have 0, 1, 1, 0, 1, 0, 0, and every time I add another bit, another one of these 1s or another one of these places, then I double the amount of space available to me. But I'm also going to want to talk about negative numbers. And if I want to talk about negative numbers, well, I've still only got the same number of wires, and so I'll have to reuse some of the wires for my negative numbers. This situation is getting worse, not better. We're getting further away from having more numbers. Okay, so now if I want negative numbers, there are a few different ways that I could consider dividing up my clock. So I could say, let me count all the way as high until I get halfway through the numbers. And then after I get halfway through the numbers, then I'm going to start again. And I'll go -1, -2, starting at the bottom. But that's not what I've done here. What I've done instead is I've said, okay, if you go clockwise around the clock, then every time you increase, you'll get a larger positive number. If you go anti-clockwise, you'll get a negative number that gets larger in magnitude as you go. So imagine we start at the 0 hand, and then I move 1 step in that direction, I'll get +1. If I go 1 step counterclockwise, then I'll get -1. If I go another step, I'll get 2. If I go another step, on the other side, I'll get -2, and so on and so forth, up until we meet in the middle. So what is the largest number I can represent if I'm following this kind of pattern? Someone new. Hania, what do you think? Yeah, so I've told you that I used to be able to count up to 2 to the 31, 2 to the 32 minus 1, and there are 2 to the 32 total spaces on my clock, right? Because I have 32 wires, and every time I add a wire, I get double the amount of numbers. Following so far? Okay, you're gonna have to hold the microphone close, otherwise it won't work. Okay, so now what I've done is I want to represent my negative numbers, and so I've split my clock in 2. So what is the largest positive number that I now have?
It should be around halfway.
It is halfway.
Yes.
So if there are 2 to the 32 spaces, what's 2 to the 32?
Divided by 2.
Divided by 2.
-1. Do you have to -1 still for 0?
Kind of, but
But like, if it meets in the middle, how do I know if it's negative that or positive?
yeah, so that's a choice we'll have to make.
Okay.
But 2 to the 32 is an even number, so we can divide it evenly into 2,
Yeah.
which gives us 2 to the 32 divided by 2 is 2 to the 30.
I don't know, I'm not a mathematician.
32 minus 1?
2 to the power of 32 minus 1.
Well, what's 32 minus 1?
Oh, 31, sorry.
2 to the 31, that's right. That's how exponentials work. So we get roughly halfway across, we get exactly halfway across by doing 2 to the 32 divided by 2, which gives us 2 to the 31. And that gives us our division point right at the bottom here. So this is essentially one way for us to decide to represent numbers. Now you might ask, why did we do it this way instead of going halfway and then starting -1 from the bottom point? And that's going to come down to what we call computer architecture. What makes the most sense for our circuitry in terms of arranging this kind of arrangement such that our circuitry does our operations most efficiently. And if you want to learn more about that, there are some wonderful classes in electrical engineering to talk about it. But 2 to the 32 seems too small, particularly when we've just cut ourselves off at the halfway point with Hania's observation that we're now only going to have 2 to the 31 numbers. Well, 2 to the 32 onto minus 1, so 2 to the 31 minus 1, because we still have that 0 there, which is neither positive nor negative. So we're really hamstringing ourselves here. So one solution to count higher is, as I think Jack said, don't remember who said it, that we could add more bits, or it's Blake. Sorry, Blake. Misattribution, there are too many of you in this little cluster here. So one solution is we just add more y's. Now, why isn't this going to be a good idea?
Something related to hardware.
Hold the microphone really close so I can hear you.
Is it something like related to the memory, something like that?
Something memory? Okay. What would happen now, let's say I need a number that's bigger than 2 to the 64. What would this solution tell me to do?
And more.
Add more y's. Okay. Now I want a number that's bigger than 2 to the 128. What's your solution? You can say the same thing again, that's okay.
And more.
Add more y's. And why is this a problem from an engineering perspective? Think about it. You've been working, I know you've been working in industry for 20 years doing electrical circuit design. What is the problem with keep adding more wires?
It needs more money.
Takes more money, yes, it takes a lot more money. Our chips are going to get bigger and bigger. They're going to consume more power. They're going to get slower as our wires as we add more wires. They're going to get more complicated. This is a crazy idea. Thank you very much for helping me with this conundrum. So 2 to the 64 is still not big enough. We haven't really solved our problem. So now let's go into brainstorming mode. And maybe, I see Rebecca over there. Let's give you the microphone. Put up your hands. Okay. I have one chunk of memory that I've used to represent all my numbers up to 2 to the 64. And I can't fit anything more in there. What's another solution that I can use? I've used up the first chunk of memory in my computer, and I've run out of space to count. What should I do?
I have no idea.
Okay, I've used up the first chunk, right? How many more chunks do I have left? Take a guess. It can be a really random guess.
10.
10. Okay, so my computer definitely has more than one chunk of memory and probably has more than 10 chunks of memory. So if I've used up the first chunk, where should I go?
The second.
The second chunk, okay. So I'm not just restricted to using this one set of 64 wires because they're just storing one variable. And so if I want to make a number that's bigger than what one variable could hold, well, what I could probably do is have a second variable and use that to store part of the number as well. So here is my proposal. I'm now, instead of going from one clock, which stores from 1 to 12, I'm going to use 4 clocks. And now, just like with our wires, if we want to figure out the largest number that we could store using 4 clocks, so if a clock has 12 different possible numbers, how many numbers do 2 clocks have, following the count of our wires?
24.
One clock has 12, so 2 is 24.
12 times.
Sorry.
If I have 2 clocks each with 12 numbers?
Yeah, 24.
Yeah, no, 12 by 12, 144, because for each position on the first clock, we can use each position on the second clock. So it's just like with our wires have 2 possible states, so with each new wire we double. If we have a clock with 12, each new clock multiplies by 12 the number of possible positions we have. So instead of having clocks with 12 positions, we have clocks with 2 to the
31.
2 to the 32 positions, really. 2 to the 31 is before we get back to 0. So we get 2 to the 31, 2 to the 31 plus 1, all the way up to we get to 2 to the 32. And so if I have 2 clocks with 2 to the 32, what's the highest I can count?
2 to the 64, is that?
Yeah, 2 to the 64. And then we can keep adding more and more clocks to get larger and larger numbers. And I would hope that my computer has more than just 10 slots for variables in it, because that might be pretty limiting for us. In fact, my computer has, I think this one has 2 to the, I don't actually even know how much memory is in that, but it's got, I think, 64 gigabytes of memory. And so if this is only, if one of these clocks is only using up 64 bits, that's just the number 64, you can do 2 to the 64 divided by 64 to figure out how many variables I can actually hold in there. But unfortunately, Rebecca, what do we have to do with most of our clocks most of the time? What have I done here?
Like when you split them, is that what you said?
Yeah, I've split them into 2 again so that I can store both my positive numbers and my negative numbers. So we've got to think carefully about how we actually use our types and how we use our memory if we want to count up to a certain number. Can everyone give Rebecca a round of applause? So you would say, well, C should be smart enough to deal with this. I never had to think about this when I was programming in Python. Ah, my poor sweet child, how naive you are. Unfortunately, if you want to count beyond 2 to the 64 in C, or sometimes, depending on the computer, 2 to the 128, you're going to start to need to get very fancy and either write code to do this yourself, or use a library that someone has written before to deal with what we call big numbers, or big integers. And we'll take a question over here. And say your name as well.
Hi. Okay. I'm sorry. Can you just clarify the difference between adding more wires and like having more memory chunks like on a hardware level? I think there's some not getting.
Sure, and what was your name?
Sarah, S-A-R-A.
Sarah, lovely to meet you. So the difference is that we have other slots in our memory. Those slots might not be used for counting the same number. So for example, imagine you have a shopping list, and on the shopping list, you're writing how much of everything you want to buy. So 3 eggs, 5 cucumbers, 4 steaks, right? And those are all going to be separate slots in your computer's memory because you're keeping track of different things. And if I suddenly go from wanting to buy 3 eggs to wanting to buy 2 to the 128 eggs, I don't know a supermarket around here that stocks that many, but let's say you want to buy 2 to the 128 eggs. Well, the slot in your computer's memory where you store the egg number isn't large enough to count that high. And so now you're going to have to use multiple slots just to keep track of the eggs. And so you're going to have to be careful about which slots are dedicated to keeping track of the eggs, which are dedicated to keeping track of the steak. Make sense?
Is it still going to be a problem if like we need to add more slots?
Well, you can use as many slots as the computer has, give or take. There's some limitations on that, but for the most part, it's okay. And you'll never run into that issue for the most part in C unless you've made a mistake in your code, which causes you to use far more of the computer's memory than is actually available. Thank you, Sarah. So our C specification is not going to give us many promises about how much memory is actually going to be given to us for each one of our different types. However, it does give us a few promises that we can expect it to obey. And this is that the types will grow in size according to this order. So a short, which is another C type, to contain just a smallish number, is at least as big as a char. An int is at least as big as a short, and a long is at least as big as an int. And a long is really just saying, okay, 32 bits or 64 bits wasn't enough, can you give me a little bit more? And it'll still let you do that. Now, depending on the particular computer that you're running, the actual number of bits, the actual number of space, and actually how high you can count with each one of these types is going to be different. So don't expect necessarily to have your code written one way and think, okay, I can definitely get to 4 billion with this variable type, because depending on the computer that you're running the code on, it might be different. That said, most modern computers tend to follow a series of patterns, and we'll talk a bit more about those later. So here are the actual rules about how much space there must be for each of these. First one, Blake. So a char has to have at least 256 values, which is enough for all the ASCII characters, and an integer has to have at least 2 to the 16, but you'll almost never see it having less than 2 to the 32.
When you say the difference between systems, do you mean like 32-bit and 64-bit systems?
Yes, but also the individual processor designs can change it. Now again, this is a feature of the specification, not of what most computers actually look like, but when writing C code, you have to be aware of this sort of thing and program your code carefully so that you don't run into these problems when someone else takes your code and tries to run it on a different type of computer. The next thing I want to talk about as well is how high we can count with floating point numbers. So these are our numbers with decimal points. So here's a question for all of you, and I want you to have a little bit of a think for a few seconds. To how many decimal places can a computer represent a random real number, so a real number from mathematics that has a decimal point in it? So give me a lower bound. At least this many decimal points. So how many I asked you for a random number, so give me a random number with a decimal point.
2.5.
2.5, okay. Do you think the computer is capable of representing 2.5?
Hopefully.
Okay, hopefully. What about if I add another couple decimal places?
Should be okay.
Okay, so how far can I keep going?
Well, I mean, if you can get to 2 to the 32, like, as a whole number, can you, like, do the equivalent of that in decimal places?
Yeah, so that's a really good insight, is that I could probably use up all of those bits to represent decimal places, except then how do I know where the decimal, where to actually put the decimal point? Do you have an idea for how I could solve that?
Do we know if it's just the decimal places or if it's like a number with decimal places?
It's a number with decimal places. It's a random real number.
Can you just have like one of the bits dealing with the decimal place? Or?
And that'll tell us if it's in position 1 or in position 0. Okay, what if the decimal place is in position 3? How many wires will I need to determine?
3.
I'll need 2 wires. So 0, 1, 2, 3, right? With 2 wires, you can count up to 3. But now we've started to run into this trouble, is the more wires I need to specify where the decimal place is, the less wires I have to actually represent the number. Now you can come up with some clever scheme to figure this out, which is what we'll talk about in one of the last weeks of class. But essentially we have this really big problem with real numbers that's even worse than the problem we had with integers. Now, how many decimal places does a real number have? Okay, Cassie, you've still got the microphone, so we're still going to go with you for this last one.
Real numbers can kind of have as many as they want.
Have as many as they want. So the number 3, how many decimal places are really in the number 3? If you're representing it perfectly accurately.
If you want to be pedantically accurate,
Yeah,
there's
pedantically.
a whole bunch of zeros at the end of it.
How many?
Infinite?
Infinite, yeah. So we've got this really, really big problem in that in order to represent our real numbers, we're actually going to need an infinite number of bits. And this tells us another point where our computing is going to break down. Can we have a round of applause for Cassie? You have a bit of a heart in there. So we've got this fundamental disconnect between the world of mathematics and the world of at least engineered computing, where we can't represent some of the things that we want to represent in a really nice, clean way, because we're just limited by the characteristics of our design. And this is where we start to think about things that are even more outside the scope of like what an ordinary computer can do. What is the largest that any computer could calculate? Okay, here's an idea. What if I get 2 computers and I use up all their slots for all the bits in both the computers? And then I get a 3rd computer and a 4th computer. Okay, I can still only count so high. And now I'm gonna fill the Earth with computers. Okay, this is not enough. I'm gonna send a spaceship. I'm gonna fill the galaxy with computers, and I'm gonna keep packing more and more bits in until the point at which the density of wires that I've got is so high that I create a black hole. So we do have this fundamental limit on how much memory we can fit in the universe based on how much computing we can pack into the observable universe, and then how dense we can make it without actually causing things to collapse in on itself. And there's some really, really interesting research papers which try and actually do this computation. What is the biggest thing that we could compute? What is the largest amount of memory that we could actually represent? We have a question from Hassan.
Sorry, I was just wondering,
Give it a second. Hold it really close.
in terms of like the limits of computation thing, would the upper bound, let's say, be like 10 to the 80?
So 10 to the 80 is probably like a reasonable guess for the number of atoms in the universe, but you don't have to treat a single atom as either a 1 or a 0. Atoms have a whole bunch of different states you could manipulate. So let's say you were able to control the spin of particles within an atom, then you could represent multiple kinds of things even with just one atom. But that's getting very far outside the scope of FOA. Maybe take an advanced quantum computing class offered at like a master's level. Would be exciting though. However, some people have actually done these calculations for us in these really fun and kind of quirky research papers that are about the ultimate physical limits to computation. What is the most computation that we could do if we killed all the people and turned everything in the universe into a computer? And the numbers turn out to be pretty substantial, but still not big enough to solve all the problems which we could actually imagine running a computer over. So like our find repeats problem, if we made our find repeats problem large enough, it could be so large that even a universe computer wouldn't be able to perform the computation successfully before the heat death of the universe and there is no life whatsoever anymore. So that's something fun to ponder about, to reflect on why are we actually here in this classroom. It's because we are very driven by both the physical and the practical limits of computing. So now that we've gone all hoity-toity and airy-fairy about the limits of computing, we will talk for a second about what our computer actually does. And the scheme that it follows is very close to what Cassie suggested. In fact, there is a long, thick manual called IEEE 754, which details a scheme for separating between where the decimal place is, where the numbers are to the right of the decimal, and where the numbers are to the left of the decimal. So we are finite, but what does this actually mean in a practical sense? Am I likely to run into problems when I start doing my computing? So let's actually see what happens when I try and do this in practice. So here is an example bit of code. This is available after class from the class, both from the class website. There'll be a link in the slides and on Ed. And here's some code that we've prepared earlier to actually show you what happens in terms of these limitations. So what I've done seems to be fairly inoffensive. I've created 3 double variables, x, y, and z in C. I have x, which is going to be just 0.1, a normal 0.1. And y, I'm just going to add 0.1 to itself. How many times have I got there? Probably 10 times. Then I'm going to do, what's 0.1 times 10? 1. And what am I doing here? 1 minus 1, what would I expect to get? 0. Okay, and then I'm just printing them out. And this funny syntax here is just to say how many decimal points I should show on the screen. So let's give this one a run. So yeah, it's visible. And I'm going to now run rounding. And remind me why I need the dot slash? Come on, a bit louder. Yeah, Blake says it's the path. The rest of you should know that by now already. Yep. James?
The dot specifies the file directory you currently in, and the slash separates that from the file you want access.
The dot specifies the current directory, and the slash specifies that we want something inside the current directory. Okay, so let me make this a little larger so you can see and be shocked and awed. Okay, so the number 1 in my computer is not actually the number 1. The number 0.1. The number 0.1 is actually 0.100000000000555. And the number y, which was our x plus x plus x plus x plus x 10 times, is 0.999999999 8898. So not quite 1 either. And then our z, which was meant to be 1 minus 1, is we get this 0.00001102. So clearly, these limits actually do matter in practical instances. Now, of course, I designed this example specifically to highlight the issues, but it's something to be aware of when you're actually writing your code, that you do not have infinite precision in your floating point numbers. Now, there are 2 types in C, and one of them I mentioned yesterday that we're not going to use is float. And the reason we're not going to use float is because it uses a smaller number of bits, and so is really imprecise, even though it is capable of representing numbers with decimal points in it. Instead, we use doubles, which have twice or double the amount of precision, but still can run into these problems. And as you work through the exercises in ED, you'll start to see ways to work around these problems and to detect them when they come up, and to know how to deal with them in a variety of circumstances. So that was our trouble.
For the float, you mentioned that it has half the space of double.
Yeah.
But can't you can't you specify how many decimal places you want for the float, and like specify as many decimal places as the double?
That would be nice, but unfortunately in C, we're limited to, remember, to the size of our clock. So a float says use a clock of typically just 32 bits, and double says use 64 bits. And when we had 32 bits, as Cassie pointed out for us, we'd quickly run out of space to specify where the decimal point is, and then we wouldn't have as much space for like how big the number is before the decimal point and after the decimal point. So C doesn't actually allow you to do that specification. You have to deal with the limits. If you want to go and deal with arbitrary precision, there are some libraries that people have written to help you do that, and then you can start to specify accurate to how many places. But this is something you have to be aware of as a programmer in general. So C has float, which is the bad one, the double, which we're mostly going to use, but there are also long doubles as well. And if you write as your type, long and then double, we get a little more precision. So let's see what happens if I do that to my code here, if we get improved results. So I'm now going to go to my code, and instead of making these doubles, I'm going to make them long doubles. Now I'm going to run my compiler again because I've changed my code, and this was called rounding.c-o to name the file. And the file's name will be rounding. Oh, okay, it's given me an error. This was actually unexpected. What does the error say? It says, oh, in order to print it, I have to use this flag. Instead of having just F, I need to have LF, because these are extra long floats. So now let's compile it again. The error should be gone. Good. And now I can see that my results have improved somewhat. They're still not perfect. Let's look at our previous ones that had 0.9999999, and then we was at the 3rd, 4th, 5th decimal place where it started to go wrong, and there we only have 4 decimal places where it starts to go wrong. So it is a moderate improvement, so it is only a small improvement, but a meaningful one nonetheless. However, we did consume quite a considerable amount of extra memory to make this happen. So this trade-off is going to be one that, if you're an engineer working on memory-limited systems, one that you might actually want to think about. So with this, I'm again going to... Who here is planning on being a maths major? Anyone? Okay, Sarah. Anyone else? What was your name back there?
Zelfin. Zelfin.
Zelfin?
Yeah.
Cool. So unfortunately, I'm going to have to ask forgiveness from both of you, because what I'm about to do right now is abhorrent to any self-respecting mathematician. But nonetheless, we will have a few questions on it. So let's assume that we are working in the world of 32-bit integers. The only numbers that exist in this world are 32-bit integers. What is 1 divided by 2?
0.
Who said that? Okay. Gonna have to keep it down for the moment to let other people think.
You could say something like 0 mod, hang on, what would be the mod? I cannot think of the top of my head. You could say like 0 maybe 2.
Okay, you could say 0 maybe 2, but is that an integer?
It's 2 separate integers.
2 separate integers, so one thing we could do is have multiple numbers to represent the outcome. What else could we do?
Just round it to 1.
We could round it up to 1 or
Down to 0.
down to 0. Okay, so those are our reasonable answers. So possible solutions, we could say that the programmer has made an error because they're trying to produce an integer from another integer that doesn't exist. Keep the microphone for a second. We could answer as if they were real numbers, pretending, which is what Python does. So if you do an integer 1 divided by an integer 2 in Python, you get 0.5, which seems reasonable. We could leave the answer as a fraction, so represent it using two numbers. So either we could leave it as 1 divided by 2, or say that the answer is 0 mod 2. We could give both the quotient and the remainder, which is essentially that answer, or give just the quotient in C. So in C, we're going to say that 1 divided by 2 is, what's the quotient of 1 divided by 2?
0.
0. So in C, 1 divided by 2, if they're both integers, is 0. You don't get any extra information, that's just what happens. So let's try this out on the computer really quickly. I'm going to change this program. You know what, I will just do it this way. And then instead of a variable name, C actually lets you here just write another bit of code that's going to get executed. So I'm saying print the integer that is equivalent to 1 divided by 2. And then we see in the corner there, I'll add another new line. And we see x equals 0. So C is giving us this very wacky and weird behavior. So Zelfin, I want you to keep the microphone. So here's another question for you, given that you are the mathematician to whom I made an apology. So now we have 1 that is an integer capped at at 2 to the 32. So that's what that funny notation means there. And I'm dividing it by a floating point number, 2.5. What is the answer to this?
If the answer can be a floating point number, then you would use a floating point number for the answer.
That's awfully polite. You should have yelled at me a little bit. This question makes absolutely no sense. Dividing an integer by a floating point number in the world of mathematics just shouldn't be allowed. So we have a few possible solutions. One is to be good mathematicians and say this is wrong, this is wrong, this is wrong. Unfortunately, too many of us are engineers and not mathematicians, so we don't take that. The next thing that we could do is we could approximate the real number by an integer, which was kind of what we did before. We said, well, 1 divided by 2 is close to 0, so let's just take 0. So we could give an integer back in return. Or what we could do is replace the integer with a real number that's kind of sort of equivalent, as long as we're ignoring how mathematics really works. So this is what Python does, and let's take a look. Now, all I'm going to do here is change one of the two numbers to a floating point number. So now I get my warning again when I compile it. Why do I get the warning? Selfin, have you still got the microphone, or have you passed it on?
Yes, we'll have it. Probably because you're trying to divide an integer from a floating point number.
So that's not what it says. It says format specifies type int, but argument has type double. What does that mean? Okay, here's a hint. You see it on the screen?
Not from here.
Oh, okay. There we go. That bit better?
Yeah. You're trying to put represent a double with but telling it it's an integer.
Yeah, Zelfin's got it exactly right. So remember, when we use format specifies, when we print things, we have to tell it what kind of thing we're printing. And we've told it we're printing an integer, but I just told you that what C is going to do is when I do something like this, when I combine an integer with a float, the answer is going to be a float. And so this also needs to be for a float. So now I'm going to compile it again. And now I get the answer I expect. 1 divided by 2.0 equals 0.5. Now I could also do this the other way around. And it would still work. And I could also do it if I explicitly created variables for them. So, okay, on F, that'll still work. And if I change that as well, it'll still work. Now notice, because I declared that f is a double, even if I leave the decimal point out here, C still knows that this is a double number, so it has a decimal point internally, and so that conversion still happens. So what's the overall lesson from these few examples? It's a trap. Types in C are complicated, and you can run into all kinds of errors. So just like we had before with our cap on the how high we could count, we also have this cap on what sort of numbers we can represent using all of our different types.
Operator, operator.
So for the last couple minutes, we're just going to talk about the few operators that we have in C. So we have a whole variety of them, and I'd encourage you to play around and use all of them in your code as you start to get more comfortable and more used to programming in C. These are all of the ones that we are going to use in class, and I'll put I'll put a copy of these slides up for you. But just like in high school mathematics, you're going to need to learn the order of precedence. So this is like BOMDAS or BODMAS, depending on which high school you learnt at. And this is going to tell us, if I use multiple operators on the same line, which operators are going to happen first. Will the multiplication happen first, or will the addition happen first? Will the things in the brackets happen first? The answer is normally yes. So pretty much universally in all systems, whatever you put in brackets is going to happen before the things that happen outside of the brackets. And the further nested in the brackets are, the earlier that thing is going to happen. And so just by following this list, you can figure out what a given expression is going to do. Now, this is also a great source of mid-semester test questions because it's very easy to get trapped by following the wrong order of operations. So just have a little practice around with these and you'll be okay. There's nothing super complicated or technical to it, it's just following these precedence rules. The one operator that many of you might not have seen particularly before is this percentage operator, and this is the modulo or remainder operator. So this is essentially going to do the same thing that we do when using the clockwork arithmetic. So if I say, what is 11 a.m. plus 2 hours? What's the answer? 11 a.m. plus 2 hours? Come on, don't even need a microphone for this one. 1 p.m. Okay. What about 1 p.m. minus 3 hours? 10 a.m. And this is essentially what the modulo operator is going to do, is it's going to do this sort of arithmetic, and it's going to tell you what you would get if you had a clock of a given size. So if you do 3 modulo 12, so that's 3 in the clock world, it's still going to be the number 3, because 3 is just at the start of the clock. But 13 modulo 12 is going to be 1, because 13 o'clock is really just 1 o'clock. And if you were to do 14 o'clock, that would be 2. And you can also do all your different operations under this assumption that the largest number that exists is 12. And so this is another way of thinking about the modulo operator. Again, the mathematicians will probably be throwing tomatoes at me for this kind of weak definition, but it's good enough for our class. And now, before we close off for the day, I just want to tell you about 2 pitfalls for order of operations. So in terms of what is happening on a line of code, if you write a line of code, there are only 2 operators that are evaluated strictly from left to right, that ignore the rest of the order of operation rules. These are the AND operator, which checks the logical AND of 2 clauses. So if A is true and B is true, and the other operator is the OR operator. So is either A true or B true? Now for an AND to evaluate to true, both sides of the AND need to be true. And what C does is clever. Because it wants to be efficient, if the first side of the AND is false, it never even bothers looking at the second side. So this can also be another source of error in your code. If you're expecting both sides to run, but C has already determined that the left side is false, then it'll never get to the right side. So precedence, these rules that we've given you, is only going to tell you what comes later and not what comes earlier in a given line of code. And that is probably enough harping on types for today. It's enough to get you started. Come back next week for a whole lot of what if. Thank you very much. Enjoy your weekends.